previous lecture we were discussing about the change in Mach number across the front of a normal shock. So, we arrived at this relationship which relates m1 square with m2 square. So, for doing the remaining algebra, which in principle is straightforward, but it is better that we walk through it so that we gain some insight. So, let m1 square is equal to x and m2 square is equal to y. So, 1 plus gamma y by 1 plus gamma x okay. So, now I will erase this and try to work out the algebra in a systematic way. So, if we multiply this, now this will be x plus gamma square x y square plus 2 gamma x y into 1 plus gamma minus 1 by 2 x is equal to, now we multiply this, y plus gamma square x square y plus 2 gamma x y into 1 plus gamma minus 1 by 2 into y. So, now we will multiply, but we will keep in mind, you know, on the left side you have one x here and you have one y here on multiplication with 1. So, I will combine together these and write x minus y. Then when this is multiplied with 1, this is gamma square x y square, this is gamma square x square y. So, you can write minus or plus gamma square x y into y minus x. Then the third term multiplied with 1, this is 2 gamma x y, this is also 2 gamma x y. So, they get cancelled out. Then we will consider the first term multiplied with the second term. So, gamma into gamma minus 1 by 2 sorry, not gamma, only gamma minus 1 by 2, right. So, this term multiplied by this term will be gamma minus 1 by 2 x square, similar term here will be y square. Then second term with the second term, this is gamma square into gamma minus 1 by 2 into x square y square, and that term will get cancelled with this term multiplying with this term. So, I am not writing it. So all symmetric terms will be cancelled and asymmetric terms will be there, and the last term is this multiplied by this. So gamma into gamma minus 1 by 2 and 2 gets cancelled anyway. So gamma into gamma minus 1 into this is x square y minus xy square. So xy into x minus y, right. This is equal to 0. So x minus y here you will get gamma square xy into y minus x, and here you get gamma square xy into y minus x on the other side, right, or do they cancel? Just check once. So hopefully we have not done any, we will get this. So let me check once. So x minus y this plus gamma square xy square minus gamma square. So where from this gamma square xy square came? This x came here. So gamma square xy square minus gamma square x square y. So gamma square xy into y minus x, that is all right. Where from this term came? So last term multiplied with last term, gamma into gamma minus 1, right. So gamma into gamma minus 1, 2 gets cancelled, it is x square y. So xy into x minus y, so they are not actually cancelling. Let us see how it goes. So x minus y plus then xy into x minus y yes, that I will take eventually, but for these two terms even xy into x minus y is common. Ideally they should have cancelled, right. So I mean at least looking into the symmetry of the term, but anyway let us see. Xy into x minus y gamma square and then this is another plus gamma square. So 2 gamma square minus, yes,
gamma square minus gamma, that will have a minus because it is y minus x.
so this will become, no, that is all right. So on this side you have y minus x, you have, if you make it y minus x, this will be 1 minus gamma into y minus x. So if you take y into y minus x as common, xy into y minus x, then you have gamma square plus another gamma square. So 2 gamma square minus gamma.
Gamma square plus gamma minus gamma square.
They are on the same side, I was just taking it, yes. So there will be only minus gamma, right, plus gamma, right. I was just always thinking it in the other side, right. So, they get cancelled, very right. So, then plus gamma minus 1 by 2 into x square minus y square, right. So, at least one term has got cancelled, even if not the full term, at least one term has got cancelled. So, gamma square minus gamma square got cancelled, plus gamma remains, this is all right. So, now you take x minus y as common or y minus x, whatever. So, 1 plus, so minus now x y into gamma all right. Now you see one interesting thing, x minus y equal to 0 is a solution to this entire problem that we have done, and here it is just a trivial solution, because if Mach number remains same across the front, that means there is no shock. So, existence of a shock means that there is a deviation of Mach number from equality from one side to the other, and that means this trivial solution. So, but why the trivial solution has come out as a part? See, we have never pre-forced a discontinuity, right. We assume that there is a front across which you have P1, P2 etc., T1, T2, but we have not assumed that they are not equal. So, they are equal is also a trivial, also a part of the solution which comes out of this. So, the non-trivial solution where there is a jump, so you have 1 minus xy gamma plus gamma minus 1 by 2 x plus gamma minus 1 by 2 y is equal to 0. So, now if you take y as common, gamma minus 1 by 2 minus gamma x is equal to minus of 1 plus gamma minus 1 by 2 x, right. So, y is equal to gamma x minus gamma minus 1 by 2 by 1 plus gamma minus 1 by 2 x, right. This will come in the denominator and that will be in the numerator, right. This minus thing will come in the denominator, right. So, how do we write 1 by y? Let me write it like that. So, y will be 1 plus gamma minus 1 by 2 x, then gamma x minus gamma minus 1 by 2, right. So, hopefully this is correct. If this is correct, then this is m2 square and this is m1 square. So, this is a general relationship between M1 and M2, okay. What about air? Special case. Gamma is equal to 1.4. that is 7 by 5. Okay. So, if you put 7 by 5, m2 square is equal to 1 plus 7 minus 1, that is 6 by 5 m2 square by 7 by 5 m1 square minus 3, gamma minus 1, the whole thing by 2, right. So, 7 by 5 minus 1 by 2. Here also, right, 7 by 5 minus 1 by 2. So, m2 square will be 1 plus, this is 5, 7 minus 5 is 2 by 5 by 2, m1 square by 5 divided by, now 7 by 5 minus 1 is 2 by 5. So, 7 by 5 m1 square plus 2 by 5 minus 2 by 5, not 2 by 5, minus 1 by 5, because there is a half here, no. So, 5 plus m1 square by 7 m1 square minus 1 m2 square. So, this is the relationship between m2 square and m1 square for air. Now, if you plot m2 square and m1 square in a graph, see, the algebra was quite tedious, but it is worth going through this exercise, because then only you can recover the trivial solution also as a part of the algebraic process. So, if you plot m2 as a function of m1, it will be a sort of a curve like this, and m2 is equal to m1 is also a solution, but m2 is equal to m1 is the trivial solution. So, that does not come into the picture in this graph. So, this is the non-trivial solution. Let us check what happens if m1 equal to 1. If m1 equal to 1, this is 6 by 6. So, m2 is also equal to 1. So, 1 comma 1 is a part of this graph, right. So, from here we can say this is m1 and this is m2. I am so sorry. This is the independent variable, this is the dependent variable. So, we can see that if m1 is greater than 1, this part is greater than 1, then m2 is less than 1, and if m1 is less than 1, then m2 is greater than 1, because 1 comma 1 is a solution. So, anything on this side the y value is greater than 1, anything on this side the y value is less than 1. So, our conclusion is that there are two possibilities around 1. Possibility 1, m1 greater than 1 and m2 less than 1, and possibility 2, m1 less than 1 and m2 greater than 1. the big question that we now raise is, are these possibilities both physically plausible or not? Fluid mechanics alone cannot give an answer to this. Even the first law of thermodynamics, which is the energy balance, cannot give an answer to this. The proper directionality of this process will be governed by the second law of thermodynamics. So, we will now calculate the change in entropy across the shock. So, we know from the first law if you neglect the changes in kinetic energy and potential energy, changes in kinetic energy and potential energy, in this problem you can doubt, you know, whether kinetic energy change is negligible typically across the shock. So, but even if it is so, you will come up with a situation where for a process where thermal parameters are governed, the change in kinetic energy will be overshadowed by the change in the thermal forms of energy. So, normally you write del q equal to du plus del w, and so let us start with that form itself. So, this has only assumption neglecting changes in kinetic energy and potential energy. Now, we will assume that it is a reversible or a quasi equilibrium process, at least quasi equilibrium. So, if it is a quasi equilibrium process, that means the process is very slow, all the intermediate states are in equilibrium. Just to calculate the properties, so it is a hypothetical process. Do not confuse the process that we are assuming here with the real process. This process is a hypothetical process that we are assuming to calculate the change in property. Once the change in property is calculated, so if you consider a thermodynamic change of state, there is a change of state from 1 to 2. This is the real process. This is what we are considering. But once we know how to calculate the change in entropy, say between these two, because entropy is a point function, it does not matter whether we have gone by this or this. So, we are choosing a reversible path where you have this equal to PdV, not only that, del q equal to TdS. And internal energy is enthalpy minus pressure into specific volume. So, this becomes dH minus PdV plus VdP plus PdV. So, you have TdS is equal to dH minus VdP. Okay. For an ideal gas, dH is equal to Cp dt and V is equal to RT by P. So, ds is equal to Cp dt by T minus R dP by P. So, if you calculate the change in entropy across the shock, if you assume Cp as constant, then it is Cp ln T2 by T1 minus R ln of P2 by P1. So, from the values or from the expressions of P2 by P1, T2 by T1 etc., this will be a function of what? M2 by M1 or function of both M2 and M1, need not be explicitly M2 by M1, but function of M1 and M2. T2 by T1, if you recall, is a function of M1 and M2, P2 by P1 is also a function of M1 and M2, and this equation tells us that M2 itself is a function of M1. So, this is a function of M1. So, now the second law of thermodynamics tells us that S2 minus S1 is equal to the heat transfer by the temperature of the surface across which the heat transfer is taking place plus entropy generation. So, the change in entropy is associated with heat transfer plus an entropy generated due to irreversibilities. If it is a reversible process, then this is equal to 0. So, now for a shock to take place adiabatically, this must be equal to 0. So, entropy generation is nothing but S2 minus S1, which is a function of M1. So, now if you plot this entropy generation as a function of M1 by plugging in the formula, you can easily use a plotting software to plot it. So, you will see this type of variation. I am trying to draw it a bit schematically, so it may not be exactly the same, but this is the magic point. This is M1 equal to 1. If M1 equal to 1, M2 is also equal to 1. So, there is no change in temperature, pressure etc. So, all the log terms will be 0. So, entropy generation will be 0. So, this point 1 you can clearly say. For M1 greater than 1, this is greater than 0, that proper substitution of the formula will tell you. Now, as per the second law of thermodynamics, this has to be greater than or equal to 0. That means this part of the graph which shows negative entropy generation is not permissible. Only M1 greater than 1 is permissible. So, possibility M1 greater than 1 and M2 less than 1, this is permissible, but this is not possible. This is governed by the second law of thermodynamics. So, a shock always converts a supersonic flow to a subsonic flow, but you cannot have a shock where a subsonic flow gets transferred into a supersonic flow, that violates the second law of thermodynamics. So, to summarize, across the shock there will be an abrupt change in Mach number from supersonic to subsonic. Accordingly, if this be the case, the pressure will rise, the temperature will rise, and you will have also the density, velocity, all the variables changing abruptly across the shock front. So, if you know the Mach number immediately before shock, if you know the ratio of Cp and Cv, you can easily calculate the Mach number immediately after shock, and based on that Mach number you can calculate all the isentropic properties immediately downstream and upstream of the shock. Thank you very much. We will continue in the next lecture.